Hello, good afternoon all of you. I welcome you all of you for active learning video lecture communication. This is the first lecture in engineering mathematics with the topic of convergence of sequence and series. This is useful for all BE semester course of semester 1. Right now it is known as calculus. Slide please, we will start with slides. Here in this chapter we will discuss sum of finitely many terms and sum of infinitely many terms. You see, sum of finitely many terms, that means consider, let us here, you say tabletop please. If I write 1 plus 2, so we can easily make the summation of these finite terms. If I write 3, then also it is easy to do the sum of this. Similarly, if I continue to finitely many terms, suppose it is 100, then by little efforts I can make the summation by simple formula, and it is 5050. Okay, when we consider sum of infinitely many terms, that means suppose if I consider 1 plus 2 plus 3 plus and so on, nth term and so on. So we have to consider that how it is possible to sum of these infinitely many terms. Similarly, let us consider one more term. One plus 1 by 2 plus 1 by 4 plus 1 by 8 2 raised to n and so on. So in this chapter we will see, or we will concentrate on sum of infinitely many terms. We will check that if we write or we take consideration in summation of infinitely many terms, then is it useful to us or not. That is our main goal in this chapter, and we will see so many types of infinitely many series. Slide please. Next, here we will define infinite sequence. Next, an infinite sequence of numbers is a function whose domain is the set of positive integers. So if I take just write, we can see on the next slide please, you can see, yes, here if we take the function f, you can see that the domain is the set of all positive integers and codomain is the set of real numbers a1, a2, a3, it is denoted as. This function is an infinite sequence, and an infinite sequence is denoted by, in general, by an, or an from n is equal to 1 to infinity. Next, here we will see example 1 of this. You see here nth term is denoted as an is equal to 2 raised to n, tabletop please. An is equal to 2 raised to n for all n belongs to n. Okay, this set n is our domain of the function or sequence. We can see that the sequence is looking like 2, 4, 8 and so on. So this is an example of the sequence, right? Next slide. In the next example we can see that nth term of the sequence is root n for all n. So here the sequence is looking like this: an is equal to square root n for all n. So it sequence looks like square root 1, square root 2, square root 3, square root n and so on. So in the second example we can see that the sequence is looking like this. Slide please. The third example we can see that nth term is minus 1 raised to n plus 1 upon n for all n belongs to set of integers, positive integers. So this looks like, let us say, here. An we have seen minus 1 raised to n plus 1 upon n. So the sequence is looking like 1 by 1, 1 by 2 with minus sign, 1 by 3 with minus sign, 1 by 4, and the nth term is minus 1 raised to n plus 1 by n. Right? Slide. The fourth example. This is little bit different that we have seen the others 1, 2, 3 examples. See, here an is equal to minus 1 raised to n plus 1 for all n. Here the sequence is looks like first term is 1, second term you can see if you put n is equal to 2, then it is minus 1 raised to 3. So it is minus 1, 1, minus 1, and so on. So nth term is minus 1 raised to n plus 1. So the fourth example of the sequences looks like this: 1, minus 1, 1, minus 1, and so on. Right? Slide please. Next. Okay. Again we see one more example of sequence where nth term is n minus 1 upon n for all n. Let us see how its sequence looks like. An is equal to n minus 1 upon n for all n belongs to n. So we can consider the sequence. When we put n is equal to 1, the first term is 0. When we put n is equal to 2, 2 minus 1 is 1 upon 2. When we put n is equal to 3, it is 2 by 3, 3 by 4, and so on. So the nth term is n minus 1 upon n. So this is an example of sequence. Slide please. Here we have seen 5 types of sequences. All the sequences has some definite behavior. The first behavior is approach to finite single value. So when we see tabletop please. Here we have seen this sequence minus 1 raised to n plus 1 upon n. So this sequence we can see that it has finite value approach. We can also put on the geometry that suppose this is 0, this is 1, this is minus 1. So we can see that the first term is a1, the second term is a2, the third term is a3, fourth term is a4. So here we can see that the approach of the sequence is going to 0. That means this sequence has a finite approach. Slide please. Now approach to infinite value. Here we have seen tabletop please. We have seen this sequence 1 plus 2 plus 3 plus n up to infinity. Here this is actually infinitely many terms. So this is not the example. Yeah, this one. Here tabletop please. In this sequence we can see that 2, 4, 8, 2 raised to n and so on. So this sequence has approach as infinity. This is actually unbounded sequence. We will see this term later on. Slide please. Next. Here we have also one example of sequence which is bouncing between the values, which I have already given to you. See here this sequence when nth term is minus 1 raised to n plus 1. Here all the terms are 1, minus 1, 1, minus 1, and so on. So this sequence is bouncing between two finite values. Okay. So next, let us see the definition. The sequence an converges to the number L if to every positive number epsilon there corresponds an integer n such that for all n n greater than n implies mod an minus l less than epsilon. If no such number L exists, we say that sequence an diverges. If sequence an converges to L, we write limit n tends to infinity an is equal to L, and we call that this limit of this sequence is the number L. Next. As we have seen the definition, let us try to prove this example with that definition. We have to show that limit n tends to infinity 1 by n is equal to 0, and we will also try to see its geometric representation of sequence on real line. So here let us see on tabletop. We want to prove that limit n tends to infinity 1 by n is equal to 0. Also we have to mention geometrically this sequence. We can see that the first term a1 is 1, second term is a2 1 by 2, and so on. So here let us write down somewhere 0, somewhere at 1. So this is our first term of the sequence. At the half of the portion it is 1 by 2, so the second term of the sequence is a2. At the 1 by 3 a3, at 1 by 4 a4, and so on. So here we can see that this sequence has finite approach, and it approaching to number 0. Now this we have to prove by mathematical calculation. So here we must show that for given epsilon greater than 0, there exists some number n which is greater than 0, such that for all n greater than n implies mod 1 minus 1 by n minus 0 less than epsilon. So according to definition we have to prove these things. Now we know that n is positive, so here modulus 1 by n less than epsilon, this we have to prove. As n is positive, we can consider 1 by n less than epsilon. Now this implies we can see that n is greater than 1 upon epsilon. Okay. Here we have to find such an integer capital N such that n should be greater than that integer. So choose integer n as 1 upon epsilon plus 1. This integer we will choose as, for example, if epsilon is equal to suppose 0.1, then 1 upon epsilon is 10, and therefore capital N is equal to 11. So this was a simple example to calculate capital integer n. So here we have to choose capital N in this way. Then for all n greater than n, we have 1 by n minus 0 less than epsilon. As all the conditions of the definition is satisfied, we can say that limit n tends to infinity 1 by n is equal to 0. So in this way we can prove by definition limit of the sequence. Slide please. One more example. Here we have considered the sequence an. The sequence is n minus 1 upon n. Try to see the geometric representation. Let us see. The sequence is an is equal to n minus 1 upon n. This was the sequence. So it is 1 to infinity. So the first term is 0, second is 1 by 2, third is 2 by 3, then 3 by 4, and so on. So on real line presentation, 0 and 1. We can see that all the steps are between 0 and 1. So this 0 is our first term. Then second term is 1 by 2. So this is A2. Then 2 by 3. So if we make 3 parts of this segment, we can see that 2 by 3 is somewhere here. So this is A3. Similarly 3 by 4. So suppose 3 by 4 is here, A4, and so on. So here we can see that this sequence is approaching to 1. So here we must show that for given epsilon greater than 0, there exists some integer n such that for all n which is greater than that number n, we have to show that n minus modulus of n minus 1 upon n minus 1 whole the term less than epsilon. Let us see on tabletop. So here we have to show, we must show that for given epsilon greater than 0, there exists n greater than 0